My name's Neha, and I lead the DCI here at the Media Lab, and I'm really excited to introduce our speaker, Ian Miers. So Ian, while doing his PhD at Johns Hopkins, was an author on a paper called Zero Cash, which was really seminal in forming what is now known as Zcash, the cryptocurrency, of which Ian is also a founding scientist. And he's currently doing his postdoc at Cornell Tech, working on various sorts of privacy-enhancing cryptocurrency and blockchain things, which he's here to tell us about today. So welcome, Ian.
Hi. So, yeah, as Nia said, this is a talk on sort of Bitcoin payment privacy and really looking beyond that to look at how you can use blockchains to solve a variety of problems in computer security and cryptography. And particularly for me, since I work on privacy-enhancing technologies, it's going to focus on things related to that, but I think it actually is quite generalizable. So I'm assuming most people in this room are familiar with Bitcoin, right? You know, it's a cryptocurrency that's worth a lot of money. These numbers, I think, are up to date as of a week ago, but it fluctuates drastically. Of course, the actual technical thing underlying Bitcoin is a blockchain, which you can think of as a peer-to-peer network that records transactions that move around funds. And its interesting point is that it's public. And so as Bitcoin has sort of gotten worth more and more money and has gotten more and more press, large numbers of people have become aware of blockchains and sort of become this fad of using it to solve all kinds of problems, ranging from the mundane to the ridiculous, where we've seen it as proposals for ways to store medical records, as a way to keep track of loyalty points for fast food, to weird commodities or things that are meant to be used for Internet of Things. And some of these don't make much sense, some of them do, and it's sort of like, what are people trying to do here? What do they think a blockchain is? And if you follow what's being reported and what people are building, it's pretty clear that at a general level, a large number of people sort of think that a blockchain is this somebody else's problem field from the Hitchhiker's Guide to the Galaxy, right? You have some problem that you want to solve, doesn't really matter what it is, and you want to make it go away by attaching the word blockchain to it. And this ranges from very legitimate problems that blockchains are well suited to ones that are legitimate but blockchains don't work for, to ones where really you're just trying to drive investment. But nonetheless, this sort of, the amount of attention this has gotten sort of tells you, blockchains really are interesting and significant, but they clearly aren't this unified, sci-fi gadget that solves everything ever, that makes all your problems go away, right? And to pick one that's sort of close to my heart, right? People, frequently think that Bitcoin is anonymous. Not so much now, though this still does go around, but certainly in the past, right? WikiLeaks, started taking donations in, I think, 2011, and said it was, an anonymous way to get payments. And we now know that this isn't the case. Not only are there academic work looking at how to de-anonymize Bitcoin, because again, the blockchain is public, you can download it and analyze what you're doing, right? There actually are companies based off of these things which looked at this research and said, what do we do if we're removed from the limitations of funding, ethics, and IRB review, and can basically do whatever we want? And they've been in business for a while. And in fact, we now know, as of a week ago, that about the time that WikiLeaks was saying, hey, this is an anonymous system, in fact, maybe because of it, the NSA was, of course, in the business of actually tracking these kind of things. And of course, now this technology is not just limited to whatever the National Security Agency can do, it's broadly available, right? These companies exist, they can do this. And so the reality of the matter is, far from being this thing you announce on Twitter as being anonymous payments, Bitcoin is in effect Twitter for your bank account, right? It announces everything you can do. Right? So this is the problem with Bitcoin, not blockchains in general, though it actually does affect those as well. But clearly this view that blockchains make everything somebody else's problem isn't true, right? They don't solve privacy, for example. And so this sort of begs the question, well, if this isn't entirely accurate, well, what is a blockchain? And to answer that question, you sort of have to think about why you're asking it. So as a computer scientist, right, one answer is we want to make better ones. And if you define it that way, then you're going to start talking about blockchains as some kind of decentralized append-only ledger, some kind of peer-to-peer network, something like that. And that is a useful way to do it. In fact, we've seen a lot of work that has taken this approach, sort of renaissance in distributed systems, with people doing huge amounts of research now on how to build better blockchains. But I think one of the other questions that we shouldn't ignore is, if we have a blockchain, if these things exist, if they really are deployed, how can we use them to solve problems? Right? And in that context, you need a somewhat different definition, because a decentralized append-only ledger doesn't really tell you what it's useful for. So the point of this talk is sort of to consider blockchains as a limited trusted third party. Right? And a trusted third party is some external entity that you trust to perform some function. And in computer security and cryptography, we frequently deal with these a lot. Right? In cryptography, we usually reduce our cryptographic primitive and prove it secure by showing that it is equivalent to some idealized functionality where we assume that some trustworthy party, sometimes referred to as like God, right, is going to do what we want, and then we show our scheme actually instantiates that without trusting it. So we already sort of work with these. In computer security, a lot of the research focuses on how do you make sure that some party that you're relying on is trustworthy, right? How do you make it harder for them to be hacked into? How do you make it so that if they are hacked into, you can find out? How do you audit what they're doing? You can sort of cast a lot of problems as building trusted third parties. So if we cast blockchains as this, we get a very interesting sort of tool we can immediately use. And the interesting thing about this is it works for a very broad definition of what a blockchain is, the underlying technology, right? You can view proof of work blockchains, as in like Bitcoin in this, as this. You can view proof of stake based ones in the same way. You can even easily view permissioned ones, which if you have any background in distributed systems is sort of classic Byzantine consensus kind of systems. Instantiate this, and then you can look at things that people probably don't traditionally view as a blockchain, where you have a centralized system that has no peer-to-peer network. It's completely trusting one guy, but it's auditable. And so this covers things like certificate transparency, where basically Google's running a log server that examines TLS certificates. So this is an interesting way to frame this, but the question is, what are the limitations, right? We've already seen that privacy is one of them. And it turns out that there are basically only two things a blockchain can do, right? A blockchain is at some level, to paraphrase Sylvia Macaulay, right, a database in the sky, right? And this means you can provide a sort of globally consistent view to everybody of, look, here's what we said happened and here's what's going on. And in most cases, right, they can enforce that this data is valid, that you can assume that if you see a message in there, that it is correctly formed. So these are useful. But blockchains can't do a number of things, right? They can't keep secrets, right? Because they are public to at least whoever's running them or to the world in general, right? They can't provide basically an anonymity of putting in transactions. You can front run transactions, you can reorder transactions, and then the last one that's actually clipped off this slide, you can in fact do any number of other things that basically break various papers people have proposed. So like insert, thing you can't do here, which is going to be someone's research idea that gets rejected. So this talk is going to focus on using blockchains as limited trusted third parties, and it's going to cover, as an overview, no real technical depth, just sort of to give you a flavor of how you might do this, two different lines of work. One of them is a mitigation of the fact that blockchains, and Bitcoin specifically, has privacy problems. So we're going to look at how you work around one of these limitations, that they can't keep secrets. And then we're going to change gears and look at something sort of completely different, which is, given the other limitations, what can you do with it? We're going to focus on sort of building fairness in multi-party computation, and then some follow-on potentials for other work. Right. So, of course, now to do this, right, let's start with the first one, right? So this is going to be Ecash, right? So Ecash, if you're not familiar with it, is sort of the term that was used for cryptocurrencies before cryptocurrencies were a thing. It dates back to the 1980s, to work in 1982 by David Chaum. And the motivating problem was that we were seeing increasing numbers of digital payments. Even in the 80s, it was clear that people weren't going to be using cash in the future at some point. And this posed a privacy problem, because unlike physical cash, digital payments are completely traceable. Right? And you can track everyone's everyday lives from this, and so people wanted a privacy solution. They wanted to make digital cash that somehow was privacy preserving. And this is a little challenging, because digital money is very easy to copy, right? Physical paper money, you can make hard to counterfeit. But if you have a digital good, you can always do Control-C, Control-V, copy them as much as you want. And so what you have to do is make them sort of unique, right? And therefore, if someone makes a copy of them, if someone tries to do what's called a double spending attack, you will be able to see that it's actually multiple copies of the same thing. But this is kind of antithetical to privacy, right? If you have unique money that's uniquely identifiable, how are you going to get privacy out of it? So this is the setting that centralized Ecash tries to solve. And this works a little like this. Assume you have a bank, and the bank has a signing key, right? And if I want to make a single unit of digital currency, a coin, I give the bank a random serial number. We're going to call it 42 in this case. And the bank signs it and sends it back. Right? Later, when I want to go spend it, I send the coin to the store along with the signature. The store asks the bank, is this a valid coin? The bank checks, have I seen this before? Right? If the answer is no, then it's a legitimate coin. Right? If the answer is yes, then someone's copied this a couple of times and it's not legitimate. The bank hasn't seen it before. They mark it down as seen. They send the store the actual money, or they credit it to their account, however you want to do this. And then the store sends you whatever good it is you're purchasing. Now, there's no privacy in this right now because this stuff is all identifiable. The clever trick with centralized anonymous cash was that you could actually remove this by using sort of magic called blind signatures, right? So you could break the link between when I took the money out and when I spent it. So this gives you privacy. This is what we would like in a system like Bitcoin, where everything that's going on here is public. Right? But the problem is this depends on a bank that holds a key, right? And so you really have to trust the bank, right? You have to trust it not to fail, not to steal your money, and not to print money, not to just inflate everything you're doing, right? Because business closes for the day, someone could take this key out from storage and just sign themselves a bunch of extra coins, right? They didn't steal your money per se, but they have inflated the currency supply in a way that eventually would devalue what you're doing, especially if they get caught and then the currency becomes worthless. And so this is a problem because basically you need to trust the bank, right? And if you're an existing bank, this isn't that bad. We trust existing banks, maybe because we don't have a choice. But it's unlikely if you're trying to do a new bank, if you're trying to do a startup, especially if it's doing a new bank with private digital money, that anyone's going to trust you, right? And you really can't get around this. You can't make this someone else's problem with Ecash because someone has to hold this key, right? Someone really has to be trusted. And so this is the problem, right? Bitcoin, on the other hand, right, is trustless, but it's not private because the blockchain is completely public. And in fact, the privacy problem with Bitcoin is worse than the privacy problem we were trying to solve with a standard bank, because in this case, the bank may, if you don't have, right, the bank may see everything you do if you don't have privacy, but you might trust the bank. In the case of Bitcoin, right, the blockchain is public to everybody. The way this technology works, anybody can find out what's going on. And so you really would like to solve this. And so, again, the problem is, right, blockchains can't keep secrets, so we can't use these techniques that require keys. So what do you do? So this is where work called ZeroCoin comes in. This is actually a predecessor to Zcash, which Neil alluded to earlier. And to build this, we're going to need a couple of primitives. You're going to need a blockchain. You're going to need commitments, which you can think of as cryptographically opaque envelopes. Right? If I want to prove to you that I know the score of the next World Cup game, right, without revealing it to you now so that you can't bet on it, I could stick it in an envelope and hand it to you. And the cryptographic properties of this envelope are going to be the case that you can't open it later until I tell you how to do it, right? So until the game's over, you're not going to be able to figure out what's going on. But once the game's over and I tell you how to open it, you will know for a fact that the data in there wasn't tampered with, right? So I didn't, wait until the game was over, find out who won, and then write down the scores of the winning teams and who was playing. And so this is useful for these kind of protocols. The second thing we're going to use is zero-knowledge proofs. And these are a little more exotic. They allow you to make a statement about some set of facts you know without revealing anything other than that statement. So for example, you could prove that you know the factorization of an integer n into factors p and q without revealing the factors. More on topic, you could prove that you know the contents of a commitment and reveal something about it without revealing all of what's in it. So I could prove to you that this envelope that contains the score of the next World Cup game, the winning team scores between 5 and 11, without actually revealing who the teams were or what the losing team score was, or in fact what the precise winning team score was. So zero-knowledge proofs allow you to do things like this, right? So going back to the centralized Ecash setting, right? If you just use Bitcoin naively and you do all these payments with Bitcoin, you get privacy, but you don't get security because this bank has to be trusted. So we need to somehow remove this. We need to get rid of the bank because we can't trust anyone to hold a key because in a blockchain, there are no parties that you actually trust specifically, right? And so to do this, we replace the bank with a blockchain. And the protocol looks somewhat similar to the original Ecash scheme, right? We still need a serial number, right? Because we still need people to prevent people from copying money, from doing double spends, from just counterfeiting as much as possible. And so you're going to pick a serial number. It's still 42, right? My random number generator for these slides is a little convenient. And you're going to create this commitment. You're going to seal it up, and you're going to send it to the blockchain along with a Bitcoin. And this is going to be stored in an escrow pool, basically. And the blockchain, because it can validate things, is going to validate the commitment's well-formed and that money is really yours, right? And then it's going to put this thing on the list. And so what happens now is when you want to spend it, you are going to generate a zero-knowledge proof that you have one of these coins in this list without revealing which one, right? So one of these commitments. And you're going to prove that that it has the serial number 42 in it, right? And so you're going to generate this proof and the serial number 42, and you're going to send it to the blockchain. And we're going to repeat the same dance earlier that the bank did. The blockchain is going to check that 42 hasn't ever been seen before, that it's a unique serial number. And if it hasn't, it's going to give you back one of these coins from an escrow pool selected at random, right? And this is not, right, necessarily the money you put in. It's just one of them. And so as a consequence of this, right, we have basically anonymized my money, right? Because this zero-knowledge proof, since it doesn't reveal which commitment on this list, right, is actually mine, doesn't tell you who I am, right? So if I'm, taking steps to hide my identity here, you don't find out what's going on. At the same time, right, so we have a private system, but do we have a system that's trustless, that's actually sound, right? Because the zero-knowledge proofs are secure, because they're sound and someone can't forge them, there's no way for me to invent money out of thin air, right? I can't just copy this multiple times, because the serial number check prevents me from doing that. And I can't, by the properties of the cryptographic systems we're using, forge this proof, right? So I really must have something on here, so which means I really must have paid the money, and I can't have copied it a bunch of times because of the serial number. So this is the basic approach to getting privacy, right? Because now, I've exchanged money that is linked to me for money that is not. The challenge with doing this is that you need to make this efficient, right? Because you actually want this to be deployable and usable, right? It's one thing to say in theory, oh, let's do this. It's another thing to try to get it to work in practice, right? So naively, if you wanted to prove that you had something on this list, what you would do is just say, either I have the first envelope, or the second, or the third, or the fourth, or the fifth, right, et cetera. This proof takes linear time, it is linear size, and unlike this Tor example, there are going to be hundreds of thousands, hundreds of millions of these envelopes on a real deployed system, so you can't do this. Right? It doesn't scale. Right? And so the basic approach in ZeroCoin was to get some kind of compact set membership proof, where you could say, look, I have this thing that is in here, but do it in a manner that is efficient. And so it's actually tricky to find this. It's tricky to get this to work. Right? A lot of details to go into doing it. But the end of it is you need to use an RSA accumulator and be very careful about how you use these things. Right? So this is ZeroCoin. Right? This gives you basic privacy because it breaks the link between when you put in money and when you take it out. But this isn't really ideal from an actual usable payment system. First of all, the proof systems proofs make it rather large. A single transaction in ZeroCoin is 25 kilobytes. The payments are fixed value, right? I put in one Bitcoin or one whatever, right? You can do this on any blockchain you want. I get back another one of those coins. I can't do fractional values. And lastly, this only allows you to anonymize your own money, right? I'm not actually paying someone here. I'm just sort of laundering money I already had that was associated with me and replacing it with clean money that's anonymous, right? This doesn't constitute a payment system. So you can take this one step further and build a thing called Ecash. And this is work done with a number of co-authors, including people who were grad students here, and I think one of them still is a postdoc. And this takes much more powerful zero-knowledge proofs and actually allows you to get payments to third parties, variable value payments. But to do it, it requires new techniques, and so you have to be very careful about it. And it's actually somewhat challenging to do. But the net result of this is if you have a blockchain, right, with payments on it. So Alice has gotten $50, right? This is actually in a commitment here from someone. And she wants to pay Bob another 10. Then what happens is she needs to say, look, I have this payment. It actually exists here, right? Because you have to point to this thing to say it exists. This is sort of how Bitcoin works, right? And then you need to basically show, look, this money is actually mine, and that the money that I'm paying out is actually less than or equal to the money that's going in, right? I haven't invented money out of thin air. This is sort of the basic constraint on financial transactions, conservation of money, right? If I have a transaction, I can't invent money in it. And then to prevent double spending, we still need a serial number. So these are the kind of checks actually that Bitcoin effectively does in a little bit different way by explicitly identifying who's paid, where the money's going, what the values are. And in fact, this is exactly why Bitcoin doesn't have privacy, because you have to identify this information. The trick in Zcash is, if you're very careful about how you do it, through the magic of zero-knowledge proofs, we can actually hide all of this information, right? The proof proves to you that this kind of statement is true, that Alice is really spending money that belongs to her, that she isn't inventing money out of thin air, and she isn't double spending it. But it doesn't tell you how the proof knows that. It doesn't reveal the information of what that money is, who it came from, or who it's going to. All you know is that this transaction is well-formed, that the new money that's paid out actually goes to someone that's correct. And so the blockchain can now validate this proof, and now the money is available for someone to spend. So this is sort of Zcash in a nutshell. This went live in October 2016. It takes about 40 seconds to complete a shielded transaction. This is the term that's used for privacy-preserving transactions in the deployed system. Partially because of this, partially because of the need of getting exchanges to adopt it. It has opt-in anonymity. So you can have unshielded transactions. You can make classic Bitcoin-like transactions on the blockchain, or you can use this anonymous system where your anonymity set is all transactions in history. Something like 20% of transactions are anonymous by value, but 8% by volume. It has greater than $60 million in transactions a day. This is a low estimate because, of course, we don't know what the actual monetary value of transactions are in the privacy-preserving part of it because it's privacy-preserving, but we do know what the amount is in the clear, right? And you can actually download and use this today. Right? And this has been sort of interesting seeing it develop and seeing it come into use. I did not think when I was starting this in 2013 and then working on this particular paper in 2014, this would ever sort of end up being deployed. And yet it actually is. And so the interesting part to me is like we've seen this pattern of newer and better cryptographic techniques that get us newer and better performance that got us from zero coin to zero cash. Right? We now have newer and better techniques that actually are going to be a new improved version. This isn't a paper. This isn't a fancy thing like that. It's just like new deployed version, which has taken transaction times from about 40 seconds down to 4, actually maybe probably less than that in the final system, and taken memory usages down from about 3 gigabytes to make a transaction down to 40 megabytes. So this has gone from being something that's kind of a pain, and you have to have a beefy computer to do, to something that's actually practical to do on a high-end phone. So I'm quite excited about that. But the point of this talk is not about Zcash or about how you actually build the nitty-gritty of this. It's like, what can you do with blockchain? So beyond just payments, what else can you do? Well, one of the things you can do is you can generalize this concept of transactions on a blockchain with zero knowledge. So you can think of this abstractly as a payment is a scheme that enforces a very basic constraint, that the money coming in is more than the money going out. Right? You could think of involving other constraints, right? Some arbitrary function f or some arbitrary function g. This is sort of a smart contract system, right? And what you can do is actually hide not just what the arguments are for what's going on here, but even what the constraints you enforced is. And so this gives you sort of private smart contracts where you don't even know what contract's being executed. So this is work we're still in the process of working on, but it's quite interesting because it's actually a little bit challenging to do this because you go from a system where effectively you only need to worry about one thing, and all of these proofs are in fact trusted, to a system where people can write their own code, they can write their own things that are going on, and therefore F and G could actually be malicious, right? G could be written to try to mess up what F is doing, and you have to make sure they don't interfere. But somehow or another, you also still have to enforce privacy and separation. So this is actually a sort of interesting problem. Beyond that, right, you can do some other things, right? You don't just have to deal with payments and transactions, right? There's this interesting thing called Decentralized Anonymous Credentials. How many of you are familiar with like EDU Roam or like Comcast, like Xfinity, roaming Wi-Fi stuff, right? You have to log into these networks everywhere you go. And so this obvious problem of whoever you're logging in with basically gets to track your location as you travel across the world or across a city, right? Because every time you log into this particular access point, you authenticate yourself. This is a privacy problem. So what if you wanted to hide that, right? And the basic approach here is instead of having coins that you pay to the access point, you could do that, right? You could pay to use the access point, pay with it anonymously. We've solved our privacy problem. But what if you don't want to do that? What if you have a subscription, you don't want to spend money individually, right? We can basically tweak this sort of anonymous payment protocol to, instead of paying you something, we merely show that we have it. And so what it will be is there'll be a coin, which is basically used to show that you can get access to Wi-Fi. Right? And this is sort of a technique that's called an anonymous credential. You can generalize this and use it in other situations, like proving that you're over 21, but not telling the bar what your name or address is. Maybe you think the bartender is creepy. You can do it for Wi-Fi. And these techniques have been around for a while, right? This exists in the centralized setting for a very long time, but it hasn't gotten much traction because existing identity providers don't really want to adapt it. And no one trusts some new fancy, newfangled identity provider that comes up and says they're going to issue anonymous credentials, right? So there's sort of a bootstrapping problem here. And so if you're doing blockchain-issued credentials, you can potentially get around this, right? You can, first of all, transform centralized credentials into anonymous ones. You can also potentially issue credentials based on things that are on a blockchain. So this is one line of these questions. What can blockchains do for computer science, right? They can sort of make electronic cash a reality, right? And by this, I mean an anonymous electronic cash, right? We've had this problem in computer science from the 1980s of how do we make privacy-preserving Ecash. Hasn't ever been able to get it deployed, right? David Chaum spent a number of years trying to get a company off the ground, and it ran into a lot of challenges because they had to get buy-in from a bank or some party who was going to say, look, we'll vouch for this, you can trust us with your money. And the business negotiations on that were difficult, and they broke down, and in the end, it didn't really take off. So you can sidestep this by using a blockchain, right? You can use the blockchain to make that trust issue somebody else's problem. You can also sort of make, you can do anonymous credentials. You can do this, zero-knowledge smart contract systems, right? And so this is basically working around this limitation that blockchains can't keep secrets. All right, so at some level, this shouldn't surprise you that much, that I said, you could use blockchains to solve some interesting long-standing problems in computer science and computer security. And what I went and showed you was a problem involving currencies, right? And of course, cryptocurrencies aren't private, but the fact that you can use them to provide privacy-preserving cash, even if it's challenging, is not, the most surprising thing at some level, right? The details are tricky, but, right? On the other hand, right, we're now going to shift gears and look at something completely different that has nothing to do with electronic cash, that is sort of using this to solve what is really sort of a set-piece, long-standing problem in cryptography. And this has to do with fairness and multi-party computation. So this is work that was in CCS this year. So if you're not familiar, multi-party computation is this idea that you have a bunch of people who have some secret information, and they want to jointly compute a function f based on those secret inputs. And what they want to happen is that everybody will learn the output of this function, y, without anybody learning the secret inputs of anyone else. So you could use this to run, for example, an auction. Say you wanted to auction off sugar beets. This actually has been done, right? Everyone submits their bids. The bids are secret because you don't want people to know what you're bidding. And the outcome of the result is who won the auction. So this is one example of multi-party computation. Another one, which has been proposed, is say these parties are like the US, France, Israel, and Germany, and they all have spy satellites. And spy satellites run in interesting orbits. You want them to be secret so that no one knows where they are and what pictures you're taking. But you also don't want them to collide with your allies, right? And so you can imagine that everyone sits down and says, look, this is the orbit of my satellite, this is the orbit of theirs, and says, look, is there a collision? And then they renegotiate this. And this actually is a thing that DARPA proposed doing. And again, right, you can see the utility here, right? We find out if our orbits are not conflicting without anyone learning where someone else's spy satellite is. So this is the theory. The problem with multi-party computation, this is a sort of long-standing thing, is that it does a very good job of keeping these inputs secret, right? No one is going to find out, exactly what you put into this function. But it doesn't guarantee that everyone finds out the answer, right? So in particular, people can abort, they can drop off the network, and it may be the case that if they are clever about it, they can drop off the network where they have the answer, right? They were like the first person that learned, and they just don't broadcast it to everybody else, right? It's a little more subtle than that, but that's the intuition. And so this is a real problem for a lot of these protocols, because for example, if you're running an auction, right, and you submit a low bid, right, you think no one's going to buy, you think it's going to be cheap, so you're going to go, all right, I'll bid $1, right, and hopefully I get whatever this is, maybe it's a car, maybe it's something else, a house, whatever, for cheap. And then you find out that, of course, you lost. And you're the first person to find out. So what you do is, you step on the cable to your computer, say something went wrong, my cat, knocked a drink on my laptop, whatever it is, right? We've got to redo the computation. And then, of course, right, this time you maybe submit a different bid, right? And so now you can start doing this trick where you sort of game the system. Or you just never participate again, right? Maybe it's a different kind of system. It's a second price sealed bid auction or something. You have to pay either way, right? Similarly, if you're doing this spy satellite thing, you could maybe game this to like start figuring out where someone's satellite is. Like you submit, your guess, like, oh, okay, I think they have it in this orbit. I'm gonna, put in exactly that orbit, and if it says collide, well, I learned that that's what it is. And if it isn't, well, you just reset the thing and try again with a new guess. So this is a real problem, and it is particularly a problem as people start trying to do these in more ad hoc settings, such as with blockchains. Right? So this is a long-studied thing. People have studied a large number of ways of doing this, ranging from gradual release mechanisms, which sort of have this, like, if someone aborts, you can, at some cost, decrypt what's going on, to restricting the class of computations you can do. This works, but the computations aren't very interesting. And then, more interestingly, there's been this notion of, well, if people abort, find them. And this work actually does use a blockchain. I'll get to more of that in a second. And then there's finally some work that uses trusted hardware to achieve fairness by enforcing timeouts, basically. And so the problem is that these don't really work. So for example, if you want to find people, right, the way this works is each party puts money into an escrow scheme. They put it onto a blockchain, in fact. And you require each party to basically stake this, and then if they abort, they forfeit their money, right? You can somehow prove to the blockchain that they aborted by very carefully constructing the protocol and the transactions. This seems nice, right? You've basically changed a computer security problem into a game theory one, and you just incentivize people not to do it. But the problem is that it doesn't necessarily work, right? It requires parties to actually have money, right? It requires, in fact, that you know how much it's worth to the adversary, the person who's going to abort, right? Like in this situation where there's an auction, right, you might know what the asset's worth. And so you can say, well, look, we're going to make you stake the maximum possible value you could have on this, right? But that's problematic. That might be a lot of money, right? In some other settings, it might not be possible to figure out what it's worth to someone. Or in some settings, it might be the case that it's known to be worth a huge amount of money. Say you're a couple of startups doing drug development. You don't have much money now, but you think your pharmaceutical is worth several $billions in the future. Neither of you can stake that much money on a blockchain to cover this fine. Right? So this mechanism doesn't quite work very well. And fundamentally, it's just not fairness, right? Like the adversary can find out what's going on and decide, oh, well, now it really isn't worth it to me to complete this, even if I'm going to eat the fine. So what happens if you want actual fairness? Right? Not just fines or time delays, but like actual fairness. And so the setting here, right, is again, we have a blockchain, which we are going to assume to be honest. And this could be a variety of different ways this is realized. And we have two or more parties who want to compute a function f, right, on secret inputs that they don't want to reveal. And we have some generic MPC scheme. And this scheme doesn't need to be any particular properties. We're literally going to say it's a generic MPC scheme, right? And in particular, we don't have an honest majority of participants, right? One of the participants, at least, is malicious. In fact, in the 2PC case, one of them is. In more cases, the majority of them may be malicious. So you can't resort back to techniques that work in an honest majority setting. And so what we're going to do is give a transformation from a generic MPC scheme into a fair one using a blockchain. And so this goes back to this sort of, OK, you've got a problem. Your problem is you're going to do this computation, and this guy's going to abort and keep the answer for himself, right? Because he's going to get it first and is going to say, well, I'm not going to tell it to someone else. And so you want to make this somebody else's problem. The naive way to do this, right, encode it in trinary or something and commit it to the blockchain, right? This is make it the blockchain's problem. This, of course, doesn't really work because the moment you put this up here, right, this guy can see this, and maybe you can actually intercept it and prevent anyone else from seeing it, right? It doesn't function, right? So what you might want to do is, encrypt it. And this is, in fact, a good idea, right? If you encrypt this thing and now it doesn't matter what happens to it, nobody can see what's inside, and so it just sort of doesn't, it's inert. But that's precisely the problem. It's inert. Like, where is the key? How does somebody decrypt this thing? Right? In order for this to work, right, the output of this computation has to be decrypted by somebody. And in fact, we want it to be decrypted by everybody or no one, right? That's sort of the fairness property. And right, you could think about, well, let's have the blockchain have the key, right? But blockchains can't keep secrets, right? And so they can't actually have a key. You can't even say, OK, we'll post the key to the blockchain so that everyone will see it at the same time, because transactions can be arbitrarily blocked, right? So this doesn't work out either. And so you need to do something else, right? And so what we're going to do is build a sort of special kind of encryption that we're going to call conditional ciphertext, which supports conditional decryption. And the way this works is you have a ciphertext which is only decryptable if you can prove that the ciphertext is on the blockchain, right? And it turns out you can do this with one of two sets of primitives. You can do this with a thing called witness encryption that is an incredibly theoretic thing that is believed to exist but isn't efficient. Or you can do this with trusted hardware, which is a thing that is actually in use today, but people have security objections to. And this is going to solve this problem. But the interesting question is, OK, if we're assuming trusted hardware, if we're assuming that we have a trusted party, right? If we're assuming that my computer is going to do what it says, why do we need any of this, right? And this is a frequent thing people run into when working with SGX and various other things that do sort of trusted execution is it seems like it makes all security problems trivial, and then you really into this question of, well, should we actually trust this? Shouldn't we do something else? And the interesting thing to me in this case is that trusted hardware doesn't solve this problem, because effectively, right, the way trusted hardware works is you have some part of your computer, some microchip on there that is going to do what it's supposed to, and it's going to do it correctly. But it's basically being held hostage by you and everyone else around it, right? It can be turned off. Someone can pull the plug on the network. And basically, there will always be an adversary you can sit between the trusted hardware and the world. And so in particular, you can't just have some trusted piece of hardware that says, look, I'll send this message out. Because what will happen is the adversary will grab it, and then they'll pull the network cable. And the trusted hardware is in your computer. It doesn't extend to actually, controlling your physical Ethernet cable or Wi-Fi. And so you can't do this with trusted hardware. And in fact, this is a formal result due to Pasch-Shalat and Florian Schwimmer in Eurocrypt in 2017. Right? Trusted hardware alone isn't sufficient. So what do? Right? Well, if you have this conditional decryption, you can, in fact, post this thing to the blockchain. And now this actually works. Even if this thing is intercepted, no one can decrypt it, because you can only decrypt it if you can prove that it's on the blockchain. So you sort of still have this inert property that no matter what this guy does, it's fine unless it actually makes it to the blockchain, and then everybody can see it, right? Because what you would do is you say, look, here's proof, here's the block this is in, here's the proof of work that this is actually included. So this works out, except for one little problem, right? This ciphertext is supposed to have some code that says, do not open unless this ciphertext is on the blockchain, right? And so this is a self-referential problem, right? Like basically, decrypt if I'm on here. And that thing itself says decrypt if, right? And it's turtles all the way down. You can't quite do this. You can't make a self-referential ciphertext. So instead, you need to sort of break this loop. And so what we do is something a little different, right? We have decryption tokens. Unfortunately, this slide, the truncation here is actually a little bad. We have these two tokens that each user has, sigma 1 and sigma 2. Sigma 1 is over here, sigma 2 is over here. And each user basically is going to have one of these things, and we're going to condition decryption not on this ciphertext being on the blockchain, but on both of these tokens being on the blockchain. And this breaks out of this loop, because now what we can do is we have this ciphertext. Right? It gets generated by the NPC. It gets distributed to both of the users. They now have it. This is shown off screen here and here. They now have it. They know they have it. And so now they go, OK, well, since I have this ciphertext, it's safe for me to post my token to the blockchain. And so both users will post it. And once both users have, now you can decrypt this thing. Because now you can feed in the proof that this thing is actually on a blockchain, and you can actually get this to work. But only if both of them have posted this thing, right? If one of them posts it, right, and the other guy's like, I'm going to try some funny business, he can't do anything because there's nothing on the blockchain to get it to work. So we've broken out of this loop, and now we have a system that does this. So the interesting bit about this is you can really build this, right? You can actually instantiate witness encryption to check that this holds. It's not going to be particularly efficient, but it is actually viable, right? And you can actually, doing trusted hardware, get a very efficient implementation. Because if you're very careful about how you build this, you can basically do it, the naive, if you know anything about cryptography, you'd think that this probably involves public key crypto. And public key crypto is a little expensive to do in MPC, right? Because MPC is like basically a very slow computer. You can think of multiparty computation as something that runs at like about the speed of like 8088 or something, right? It's not fast. But if you do this in symmetric crypto and you're very careful about how you set the system up, it basically adds almost no overhead to whatever MPC calculation you're wanting to do. So this really practically solves a problem, right? This gives you fairness, with some caveats I'll get to, in a way that's practical and efficient by making sort of the, this problem of how do you distribute these answers sort of somebody else's problem. You outsource the fair bit to the blockchain. And the interesting point here is like blockchains exist. They actually are deployed, they're actually used. And so this isn't like some theoretical, oh, if you had some weird kind of left-handed unicorn, right, and we got this to be useful and got it deployed, this would work. This is like a you can use this today kind of thing. So this is like in my mind, really sort of the power of using these kind of techniques is you can get things that are actually practical. Of course, there are some caveats, right? This really does make some things somebody else's problem in a way that isn't clear that they're entirely solved, right? You only get fairness, right? You only get the guarantee that this guy doesn't get the answer unless this guy does if you can't forge the blockchain, right? You can't forge a proof that something is on a blockchain. And so for proof of work blockchains, that's true in the short term, right? It would take me a very long time to forge a couple of blocks in Bitcoin. But eventually speaking, I will be able to do it, right? In like 1,000 or 1,000,000 years, right? And for some settings, that may not matter. If you get the outputs of like, an auction that's being run today in 1,000,000 years, who cares? For some things, maybe it does, right? For proof of stake-based blockchains, there are other problems with like committees can sign things and such. For proof of work, if you're using trusted hardware, you can have sort of a timer, right? Where your trusted hardware goes, well, you have X number of days to submit this proof, and we assume you can't forge something in those number of days. So again, this gets you fairness, right? Which is sort of a long-standing problem with which there were, in fact, impossibility results that you can't do it. This doesn't break them, it just sort of sidesteps them by making the trusted party like this decentralized sort of nebulous blockchain. So where do we go from here? So this is sort of the interesting part to me, which is we have these two kind of things, right? Where we have witness encryption, which is sort of a theoretical primitive. We have even things that are more exotic, like I/O and maybe even VBB, to the extent that people still think you can do that. And we have trusted hardware. And these are things that exist today. I mean, you probably, if you have a phone, actually have some kind of secure cryptographic code processor in it, right? But all of these things are actually, they're quite powerful, but they're still limited. They actually themselves are a limited trusted third party, right? Because, as I said, they're basically being held hostage by the device they're on. You can do all kinds of funny business to them, right? And the interesting bit is we can think of blockchains sort of as complementing this, because blockchains have also limitations, right? They can't keep secrets. They can't provide anonymity. You can do all kinds of weird things to them. But trusted hardware can keep secrets. It can provide some degree of anonymity because you can make sure that things don't happen unless other things do. At the same time, can't do some of the things blockchains do. You can't get a globally consistent view. This is why trusted hardware doesn't work just for fairness. And in a lot of cases, you can't keep state very well, right? This is just sort of an engineering problem. Some of these things do it well, some of them don't. So you get all kinds of attacks. And so the interesting thing in this case is that you sort of have these sort of two complementary things where these have some weaknesses, these have some weaknesses, but if you combine them together, right, you can actually sort of get something that's stronger than either of them individually. So where do you go from here, right? So in general, and this is a little hard to formulate, right, you can use a blockchain to keep state. You can use it to do input and output, basically do communication. You can't use it to do secrets. You can use witness encryption, trusted hardware, I/O, et cetera, to keep secrets and to compute on secrets. But you can't get them to keep state because they can be reset, right? If you have this cryptographic thing that's like just a blob, you could always like rerun it again in parallel. And you can't get it to really do output. You can't get it to guarantee to communicate with anybody. But if you combine them, you get the sum total of these things and can get really sort of strong protocols. You can get censorship resistance, and you can synchronize state across things. So what does this look like? Well, a couple of interesting things you can do with this. One of them is you can do password-based disk encryption. So for your phone, we've gotten pretty good at encrypting data on phones, even though people can't remember strong passwords, right? Like my phone has like a 5-digit PIN number on it, which is very easy for someone to brute force and like, you just keep trying every guess. And if all you have is just an encrypted blob, this will take you a couple of days maybe. So what we have done, what people like Google and Apple have done, is they've started using trusted hardware. And so what happens is your phone isn't encrypted under some key derived from this PIN number. It's encrypted under some key that's stored in trusted hardware. And in order to get that unlocked, you have to put in the PIN. And the hardware keeps a little counter that says, look, you get 1 guess, 2 guesses, 3, 4, 5, and then either it's going to slow you down or delete the key and actually delete everything, depending on how aggressive it's set up. And this is really useful. It's very good at securing your data on your phone. But the problem is that it doesn't do very well if you destroy your phone, right? Because the key is living in hardware, right? And so if I have some encrypted backup, and I've destroyed the phone, I can never decrypt it. And the interesting thing with if you do this like witness encryption plus blockchains is you can actually get around this problem. You can build a piece of software, basically, that isn't tied to a physical device, that can't easily be destroyed, which still has this property that it provides strong security using a password, even if you use a weak and short password, something you can actually remember, and not some crazy 128-bit random string. Right? So this is one thing you can do. One of the other things you can do, which we're starting to look at, is you can do interesting things with running sort of exchanges and managing cryptographic keys for cryptocurrencies, where you have like a set of enclaves that need to communicate in a way and make sure states synchronize between players, and they use the blockchain as a way to actually do this and prevent aborts and even like selectively downgrade access control structures if someone like dies, for example, isn't available. So yeah, that's sort of the end of the talk, at least of the slides I have. So for that, I'll take questions, comments, rotten vegetables if you have any, et cetera.
So in the case where you have each person has to submit a token to the blockchain to unlock some data, how do you guarantee that one of those people aren't just running a local copy of the blockchain on their computer where the other person can't see?
So that comes into the can you forge the actual block. So take Bitcoin, for example. Right, you'd submit it, but you couldn't actually get the proofs of work that actually happened on the blocks because you don't have enough computational power yourself to do that. Right, so unless you broadcast it to the world, it's not going to get mined. It's not going to get included by a miner, and so that block won't look legitimate to this piece of trusted hardware because it won't have the requisite proof of work on it. It won't have confirmations. Right. Now, if you have an unlimited amount of computational power, this doesn't hold, right? So this is the weaker assumption, right? You've moved this from a situation where you wanted fairness from an unbounded attacker, well, so from a polynomial bounded attacker to an attacker who has far more strict computational limitations. Because technically, if your attacker has polynomial computation, they can do any of this stuff anyway.
You mentioned that the MPC circuit hardware is slow. You'd imagine that would be some incentive from hardware manufacturers to speed that up. Is there a theoretical limitation there, or is it?
So there is some incentive. It's not. It's kind of funny. So basically, people have done a lot of work of optimizing. In fact, the reason this thing is fast is because people have done a lot of work at optimizing some very basic primitives. There is some work with Intel on trying to give them the basic instructions they want to do faster stuff. It involves doing a particular way of keying AES. I mean, Intel chips have hardware accelerated AES instructions, but they don't have the key schedule. It's not quite the right thing. So there is some talk about doing that, but the last time I heard of this, someone was complaining that Intel wasn't actually interested. But I don't have the context as to why, and I don't know if that's still the case.
What's the classic problem you could solve with that multi-party computing? Because that's a scary graph, isn't it?
Wow, the size of these things? Yeah, so the class of problems in theory is, anything you want, right? They're Turing complete. The more interesting question is what's the class of problems you can solve efficiently? And this is a very large open research question, the one I'm actually not that much of an expert on, right? This is literally, we sort of picked an arbitrary benchmark from one of the systems to show that, look, it's, the overhead's minimal, but the actual cost of doing what you want is actually somewhat high. People have gotten things that are practical for some settings, like if you're doing data analysis and you only need to run the computation once, like it doesn't matter if it takes a couple of hours. So for example, there was a project that took data from, I think it was the Estonian Tax Authority and Estonian health insurance, and wanted to do some things about economic well-being and longevity or some such studies. And by law, these data sets can't be shared. But you can do a multi-party computation between both parties where no one else learns it, but you get this whatever metric it was they were computing. And that was actually practical to run, but it may have taken a couple of hours. On the more sort of efficient side, Didac changed their name, but the company has actually MPC for doing signatures for Bitcoin, for blockchains, somewhat efficiently. I don't have exact numbers, and I think it was like less than 5 seconds to have two parties compute an ECDSA signature using under some set of assumptions, probably like the best they could get to get it to work, but it still like exists.
I kind of had a high-level question about trusted hardware.
Yep.
I'm still not quite sure how to really think about trusted hardware, and in particular the threat model of trusted hardware, and you know, are there going to be many more sort of vendors, and people are going to be using different vendors, so it's not all like Intel has access to all the private keys. And you know, this is kind of a little bit of a high-level question, but I'm curious, like, how should we be thinking about trusted hardware and how that's going to evolve in the future?
So I think the first answer is to think about it as something where you can replace the trusted hardware bit, right? So that's sort of the interesting way I like this formulation is we have this sort of generic thing that is either this, frankly, somewhat theoretical and not quite practical yet, cryptographic primitive that maybe gets there, or trusted hardware. And then we can sort of say, look, we're going to build this, and if you want this, these are the only two ways you can get it, and you sort of decide whether it's worth it or not. On a more practical level, I think it is the case that we're starting to get more diversity on these kind of assumptions. Azure or Microsoft built this sort of platform which abstracted over Intel's SGX stuff and gave it sort of generic API. And if you read between the lines and you ask the right people after they had enough beers that they don't care about their NDAs, they will tell you the obvious implication, which is not just as Microsoft building an API to abstract over, you know, SGX. The next logical thing is of some guys over here who are building a new version of trusted hardware that they have that's going to go into their data centers. And so we're starting to get a point where a couple of people are building these things. But yeah, there isn't really a good notion of what these trust assumptions should be. No one has a notion of how much money it costs to get into these things. I've heard numbers that it's like $5,000 to pull the keys out of an SGX enclave if you really know what you're doing, which is exactly like way lower than you'd think. But this is from someone whose name they didn't want to be public, but if I told it to them, told you, you'd probably believe me.
And are these different? Is trusted like are these things compatible? Like, can you? Is there anything keeping you from having systems where people have, like, I want to trust AMD, you want to trust Intel, fine, but we can still work together on the same system or computation?
It depends, right? Because you can run into this problem if you, especially if you're doing this on a blockchain, right? Where, say, you know, these two tokens both came from trusted hardware, you could end up with a problem where like one of these is from AMD, one of these is from Intel, and you know half the blockchain doesn't trust Intel or doesn't trust AMD or something, and so you could end up like in a weird, like, we don't know how to validate this transaction because we don't trust the person who authored it. But in principle, it is possible for a lot of other applications. You can just, you know, do sort of the multi-sig analogy of, look, run it 3 times in each one of these things, right? And that probably should be sufficient. But then you have to have everyone's hardware, right? So it's a little cumbersome. In cloud settings, that probably works out, though, right? It's not really that, you know, provision 3 instances instead of 1, whatever, right? Instead of I have to have 3 phones and 3 laptops. Anybody else?